All right, y'all. We're going to go ahead and do a quick video on 2.6. 2.6 is going to be talking about combinations of functions. The first thing that we're going to do is we're going to start by talking about a reminder of domain on functions. We'll read through this quick blurb here and then we'll do some examples. Domain of a function, all values of x, which a function is defined, doesn't break any rules. For example, we exclude from the domain all numbers that cause division by 0 or a square root of a negative number. And these are really going to be the two instances that we have to check for in each of these problems: a division by 0 or a square root of a negative number. If we don't have either of those issues, then we're going to be fine and we're going to say that all real numbers are going to work for the domain. But we have to check these issues in each of the problems that we're being presented. So let's look at some examples of seeing if we can identify any domain issues. The first one that we're going to look at is f of x is equal to x squared minus 7x. Notice that this one doesn't have any square roots in it, and it also doesn't have any divisions by 0. There's no x's in the denominator. So because of that, all real numbers are going to work. So we can say the domain is negative infinity to positive infinity, also known as all real numbers, because there is no division by 0 or negative inside square root, because there are no square roots or there's no x's in the denominator. So that one is one that's kind of easier to check. Let's look at one that might give us an issue instead. This one says g of x is equal to 5x over x squared minus 49 minus 5x over x squared plus 49. Okay? Well, here, notice that we do have a potential issue with a division by 0. We don't have any square roots, but we have a potential issue in the denominator of these guys. Because we have x's in the denominator, we're always going to have a potential for there to be a division by 0 issue. Well, think about this right one for a moment, x squared plus 49. This denominator right here is never going to be 0, because any number that you plug in to this x squared function is going to be positive. Any positive number is going to be positive, because whenever you square a positive, you get a positive. Any negative you input is going to be a positive, because when you square a negative, it's positive. Any positive number plus a positive number is already going to be just a bigger number at the very least, right? So this is never going to be 0 in the denominator over here. The problem is, though, this has a potential to be 0, specifically when x squared is going to give us a value of 49. The way that we're going to check for values that actually give us the areas that we want to avoid, or the values that we want to avoid, is we're going to set the denominator equal to 0. So whenever you're worried about a division by 0 issue, we set denominator equal to 0. So for example, this one, what we'll do is we'll take x squared minus 49 equal to 0, and I'm going to put and solve, and then we'll solve for what values of x makes this true. Well, we can add 49 to both sides first, and we'll get x squared is equal to the square root, or sorry, apologies, I got a little bit ahead of myself there. X squared is equal to positive 49, and then to get rid of the square, we can take the square root of both sides. So we'll do excuse me, square root of x squared is equal to plus or minus the square root of 49. Remember to include that plus or minus like we talked about in class last week. And we'll say x is equal to plus or minus 7. So that means that there are two potential values that are going to lead this expression up here to be 0, plus 7 and negative 7. If I go back up, then that means that that would make this expression in the denominator 0, and we'd be doing a division by 0. So this means that we want to actually avoid those two values. So for the domain, we want to have all real numbers except for negative 7 and positive 7, because those are the two values that are going to make this a division by 0. The way that we're going to represent this is we're going to start at negative infinity, we're going to go all the way to negative 7, but we're going to skip over it. And the way that we're going to do that is with the set union notation. Remember, we use a bracket to include a number and a parenthesis to exclude it. So we're going to write -7 on either side, but the parenthesis is going to indicate that we're not including it. And we want to do the same thing at 7. So we're really going to have 3 intervals that work for us then. We're going to have the interval from -∞ to -7, everything before 7, -7 rather. Then we're going to have everything between -7 and +7, and then everything past 7. So really we're just going from -∞ to infinity, but we're hopping over -7 and +7 right here. But this would be the answer for our domain. Okay? Let's go ahead and look at an issue with a square root. C, we'll look at, excuse me, h of x is equal to the square root of 9x minus 27. Here we don't have a division by 0, but we do have an x inside of the square root, which means that we're going to have a potential for a negative number inside of the square root. To avoid this, we're going to set up an inequality to make sure that any value of x is going to lead to an expression that is greater than or equal to 0. So what we're going to do is we're just going to isolate the piece inside the square root, 9x minus 27, and we're going to set that piece greater than or equal to 0. If we solve this inequality for x, it's going to show us the x values that are going to make this expression positive right here, or equal to 0, which is the ones that we want for this. Any negative expression is going to lead to something that we don't want inside the square root. So let's go ahead and add 27 to both sides and start solving this. We'll get 9x is greater than or equal to positive 27. Dividing both sides by 9 gives us x is greater than or equal to 3. So then we have here, the x has to be greater than or equal to 3. And these are the values on which this function is going to work. So the domain then, if you were writing it in this inequality notation, you could just leave it at this. But remember, we like to write things in interval notation. And to represent all numbers greater than 3, we're going to say 3 to infinity, including 3 with the bracket, and then with the infinity always just leaving it as a parenthesis, okay? And that would be the domain. If we chose, let's just think about choosing a number outside of the domain for a second, like 2, then 9 times 2 would be 18. 18 minus 27 would be -9, and then -9 wouldn't work because I'd be taking the square root of a negative number, right? That's why we have to have only numbers strictly greater than 3, and that's why we set up this inequality to show us what works here, okay? Let's look at one more where we might have a potential double issue. D. This one says j of x is equal to 3x plus 2 over 14, the square root of 14 minus 2x, okay? Notice that this one has a potential issue for both. We have a square root, but we also have a x in the denominator, so we actually want to do both checks. I'm going to do a division by 0 check here, and we're going to make sure that we're not dividing by 0. And then we'll also do a negative inside the square root check. Let's do the division by 0 check first. Here, remember the strategy that we took for this is we took the entire denominator and we set it equal to 0. We then solved this piece to figure out what values of x would lead to 0. Well, I can square both sides and get 14 minus 2x is equal to 0. I can add 2x to both sides and get 14 is equal to 2x. And then I can divide both sides of this equation by 2. And that leads to x is equal to 7. Now, we've solved for x is equal to 7, but remember what this means is that this is going to make this expression up above 0. So that means that we want to avoid the value 7 in our domain. So that's going to be one piece of information that we have to carry on with us whenever we're thinking about writing the domain. For the negative inside the square root, remember the strategy that we took for this is we took that inside of the square root piece and then we set it greater than or equal to 0. This is going to show us the possible values that x can be in order to keep that square root positive. We can go ahead and solve for this. This time I'll maybe subtract 14 from both sides just to keep the x on the left-hand side. I know that some of y'all like to think about the inequalities with x always on the left-hand side. And then we can go ahead and divide by -2 on each side. Notice here that because we're dividing by a negative number, we have to reverse the direction of the inequality. So that means that x has to be less than or equal to 7, not greater than or equal to 7. And now we have two pieces of information here. We have, for it to be negative inside the square root, that x has to be less than or equal to 7, but also we saw that at 7 we had a division by 0 issue. So really, all of these numbers work besides for x being equal to 7, which means that our domain really just needs to be x is strictly less than 7, not x is less than or equal to 7. So for our domain, compiling the two pieces of information that we see below, we can say that we can include all the numbers from negative infinity all the way up to 7, but not including 7 itself, right? So x can be less than 7, but it cannot be equal to 7, okay? That's going to be all that we're going to do for our discussion of domain on functions. Remember, there's really just those two important issues that we need to look at. If it doesn't have any division by 0 potentials or any negative inside the square root potentials, then we're good to go ahead and move on, okay? Let's look next at some algebra of functions. In other words, how can we combine functions with one another? And there's really 4 different types of ways that we can do it that coincide with the typical ways that we actually combine numbers. We can either sum functions by adding functions directly, take the difference of functions by subtracting one from the other, take the product by multiplying them, or take the quotient by dividing them, provided, again, just like with regular numerical arithmetic, that the underlying domain is not 0, right? That g of x is not equal to 0, okay? The domain of a combined function is a set of all real numbers common to both of the functions, okay? This is going to be helpful for whenever we're kind of looking through the domains of combined functions in general. But let's look first at some examples of combining functions, okay? Example 2. Example 2 says we have f of x being equal to 2x minus 1. And then we also have g of x being equal to x minus 10. And then we're asked to find each of the following. And I should have probably labeled these, but I'll go ahead and label them now. First, we'll look at f plus g of x. Now, typically on the homework situation and on the exam situation, they'll probably ask it in terms of this f plus g of x notation. I would, if I were you, recommend writing it in terms of the equivalent notation, f of x plus g of x. I like to think about it in terms like this definition up here says, because thinking about it in the right-hand side makes it really clear to me, at least, that I need to just substitute in what I see for f of x, substitute in what I see for g of x, and then simplify. So here, if I'm thinking about what f of x and g of x is, well, f of x is 2x minus 1, and g of x is x minus 10. So that means, if I simplify this, 2x plus x would give me 3x, and then minus 1 minus 10 would give me negative 11. So f plus g of x, whenever I add those functions, is just 3x minus 11. Okay? Let's look at the function difference. If I do f minus g of x. Okay? Well, if I do f minus g of x, again, I would recommend thinking about it in terms of f of x minus g of x, because then I can rewrite it as 2x minus 1 minus x minus 10, right? Now, we do got to be careful right here, because we want to make sure that this negative sign gets distributed to both of the things inside that parenthetical set. So what I'll have is 2x minus 1 minus x plus 10. And then whenever I combine my like terms, it looks like what I'll be left with is just x plus 9. And then that would be it for f minus g of x. Okay? Let's look at some of the more complicated ones. C is going to be fg of x. Again, I've said it before, but I'll say it again. I would prefer thinking about it in terms of f of x times g of x, because then this tells me that I need to write it as 2x minus 1, what my f function is, times my g function, x minus 10. Again, I'm using parentheses here to make sure that I'm setting up this distribution properly. Notice that this is setting me up for that FOIL method that we talked about earlier, where you have to make sure to multiply all 4 things that are being paired up here. 2x times x, 2x times 10, negative 1 times x, negative 1 times negative 10. Whenever we do that multiplication, we'll get 2x squared minus 20x minus x plus 10. And then we can combine like terms to get 2x squared minus 21x plus 10. okay? And that is all that we can combine. Now, making a quick revisit to each of the previous problems that we did, an important thing to kind of look at is what the domain is going to be for each of these guys, right? And the domain, remember, is just what works for both of our original functions. Well, notice that in both of our original functions, we don't have a division by zero issue or a square root issue, which means that the domain for every single one of the functions that we've talked about so far is going to be negative infinity to positive infinity. So if we wanted to quickly go in and write that for all the functions that we've talked about so far, we absolutely could, right? All of the domains so far that we've talked about would look like negative infinity to positive infinity. The only problem is whenever we get to this last one, we're doing a division, so we have to be a little bit more careful. What we're asked to do with this last one is f over g of x. And what this really means is that we're doing f of x over g of x. And whenever we make that substitution, the 2x minus 1 over the x minus 10, then all of a sudden we have this potential for 0 in the denominator here. Notice that this is really about as simple as we can get it. So this is f over g of x. But as far as the domain goes, we have to make sure to exclude what would make this 0 in the denominator. And here you can see that it would be the value 10, right? So it would be negative infinity to 10 union 10 to infinity, right? So it's really easy to kind of look at the domains for the previous ones, but this one we have to do a little bit more work once we look at the final version of the function, okay? That's what we're gonna talk about for the function arithmetic. We have one more idea of how we can combine functions in this section that we'll quickly go over, and it's the idea of composite functions. Composite functions are gonna be basically a fancy way of saying we're gonna plug one function into another. They're represented by this function notation symbol right here, f of g of x, or sometimes some people say fog or goff, and it's equal to just g of x inputted into f of x. To find the domain of f of g of x, we first exclude all x not in the domain of g, then we exclude x for which g of x is not in the domain of f, and we'll talk about that a little bit more in a moment. First, let's go ahead and work through some of the examples of just generally combining these guys. All right. We'll do example 3. And we'll probably do example 4 as well, but we'll probably leave 5 up to y'all if y'all would like to look at it later. But for here, we have f of x is equal to 5x plus 6. And we have g of x is equal to 2x squared minus 1. Okay? What we would like to look at first is f of g of x, excuse me. So, since we're looking through this right here, what I would recommend doing, just like we did whenever we were looking at the function arithmetic, is I would recommend that we look through the function through this lens right here instead, right? Use that definition to say f of g of x is f of g of x. And the reason why I prefer looking at it like this is because this tells me that I need to input g of x inside the f function. G of x is just 2x squared minus 1. So what this means is that f of 2x squared minus 1 is what I would want to evaluate then. This tells me that I need to input 2x squared minus 1 into the f function up here. So everywhere where I see an x in the f function, I'm going to replace it with a 2x squared minus 1. So notice really what's happened here is I have what looks like my f function, 5 times something plus 6. But the input that I'm using here is the g function itself, this 2x squared minus 1. We can go ahead and do some distribution to simplify if we would like to, but this is really f of g of x right here. We can go ahead and distribute to get 10x squared minus 5 plus 6, or 10x squared plus 1. And this right here is the definition of f of g of x. Notice here, we don't have any issues present in the domain of either of these guys, so our domain would just be negative infinity to positive infinity, okay? So this is f of g of x. Let's look next at g of f of x. Again, I would recommend kind of first rewriting it as this function notation, g of f of x. That lets me know that I need to start by plugging in f of x into g of x. F of x is 5x plus 6. And then that means that I need to plug in 5x plus 6 into my g function up here. So that means that I'll have 2 times 5x plus 6 squared minus 1. And that would be plenty of information for my g of f of x function right here. Now, if it asks you to simplify fully and kind of go through through that, you'd want to make sure to do that distribution. But for here, we'll kind of put a pin in it right there and say that this is that function substituted into it, right? This is kind of the harder part to see than actually doing the distribution that we already know how to do. One thing that we can still talk about is whether or not there's any domain issues. Again, there's no domain issues with f or g because I'm not doing any division by 0 or negative inside the square root, so I'm not going to have any issue with this potential piece as well. So I'll go ahead and leave this alone right here. The last thing that we'll talk about for this one before we move on is how we can evaluate actual function inputs at this composition function that we have right here. And the first one that it wants us to look at is f of g of 2. And again, we can think about this in one of two ways. You can think about this either as plugging into the f of g function that we found up here. Let me go up a little bit. Into the f of g function that you had up here. So you can plug in 2 for this x squared right here and then follow that arithmetic. That works really well if you've already kind of done the algebra to get this piece right here. But if you don't have this piece, what you could do instead is you could do f of g of 2 and then evaluate g of 2 and then use that to evaluate f. For example, g of 2 would be 2 times 2 squared minus 1. Well, 2 times 2 squared, that would be 8, and then 8 minus 1 would be 7. And then I could do 7 and input it into the f function, okay? Well, f of 7 would be 5 times 7 plus 6. 5 times 7 would be 35, and then plus 6 would be 41. And notice that we would get the same thing if we were to plug it in directly to the function before. If this is f of g of x, then we get the same thing if we were to plug it into the function up above. If I plug 2 into this function right here, then 2 squared would be 4, times 10 would be 40, and then plus 1 would be 41. So you can do either of those methods right there. Either way, you'll get to this value of 41, right? Wonderful. Let's do one more of these. Let's go ahead and do example 4. And look at some potential domain issues that might arise. Here we have f of x is equal to 6 over x. And we have g of x is equal to 3 over x. Notice here that we immediately have some potential domain issues because we're doing division by 0, right? We need to avoid x is equal to 0 in both of these cases because it's going to lead to a problem for us, right? So let's go ahead and see how that's going to look with some of this domain issue stuff. First, let's look at f of g of x. F of g of x here, again, is just f of g of x. And if we plug in f of g of x, or if we plug in g of x into f rather, what we get is f of 3 over x. So what this means is that we need to have 3 over x as an input for our f function. This means that we're going to have 6 over 3 over x. We got to be a little bit careful with all of the fractions that we have in this case, right? Notice that here we have a fraction over a fraction. In general, what I'm going to recommend doing, especially if you have multiple fractions in this case, I'll make a note off to the right over here, is if you have something like a over b all over c over d, then I'm going to recommend that you rewrite that as a over b times d over c. Because dividing by a fraction is the same thing as multiplying by the reciprocal. That's a little bit of knowledge that we should have seen somewhere in the past, but if not, it's a good reminder to have it here, right? In general, what this means is that if you have something that looks like this, you can rewrite it as a times d over b times c. And that will be very helpful for us. Because what we end up getting here is if we're treating 3 over x as our c over d, then we'll have 6x over 3. Or if we do that division, then that would just be 2x. F of g of x. Now notice by just looking at the simplified version of the f of x or f of g of x function that we have right here, we would never suspect that we would have any domain issues with this because 2x doesn't have any divisions by 0 or any square root issues in it. But the problem is with how we've gotten here, there are some potential domain issues. Specifically, we have a division by 0 that's possible right here. So the domain for this function still has to avoid that 0 value that we talked about. It has to start at negative infinity, go to 0, but skip over 0 like we had with those other division cases, okay? Oop, zoomed out for a minute. There we go. Wonderful. So we do got to be a little bit careful there in that instance, okay? Let's look at example 3 real quick. Or sorry, let's go on to the next part of this example rather, the g of f of x. If we do g of f of x, then we'll have g of f of x. And we're basically just going to be doing the opposite of what we did last time. We'll plug the f of x function into g. And that means that we'll have 3 over 6 over x. And whenever we do the simplification, we'll have 3x over 6 or 1/2 x for g of f of x. Again, looking at this, you would never think that there was an issue just with this piece right here, but because we had potential division by 0 issues up here, we still have to say in this, the domain that we're going to exclude 0. So negative infinity to infinity, and then also 0 is excluded. So negative infinity to 0, union 0 to infinity. Sorry, I recognize that my recording device is dying, so I was trying to get through this one. Okay? Wonderful. Let's really quickly look at what happens if we wanted to plug in maybe a specific number into this. So if we did f of g of 2. Well, before, we saw that f of g was just 2 times x, so that would be 2 times 2, which would be 4. If we did g of f of negative 1, for instance, then it would be 1/2 times negative 1, because this is what we found to be g of f, and that would be negative 1/2, right? So after you've solved for them algebraically, plugging in concrete numbers into them isn't entirely so bad right here, right? Let's talk really quickly about example 5, and then we'll be done for this section. Example 5 has f of x being equal to the square root of x, and g of x being equal to x plus 2. Okay? If we look at what's going on here, and we start trying to figure out f of g of x, then what this is asking for is to plug g of x into f of x, but g of x is x plus 2. If we plug that in as our input for f, then we'll have the square root of x plus 2. Notice for this one, we'll have to be a little bit careful with our domain. I'll let you go back and check that like some of the other previous examples, but really you just want to make sure that this inside expression is going to be greater than or equal to 0. So to find the domain for this, you'd have to set x plus 2 greater than or equal to 0 and then solve that expression, right? If we wanted to do g of f of x, then we would want to do, again, g of f of x, which means that we would want to input the f function, the square root of x, into g, and what we'd have is the square root of x plus 2. So g of f of x is equal to that business right there. Again, we have that potential division by, not division by 0, negative inside the square root issue. So to find the domain, just like we did in this one up here, if you wanted to find the domain, you would have to solve the x being greater than or equal to 0. And notice that this is actually already solved for x, so that one's not so much of an issue right here, okay? Wonderful. Other than that, the inputs of the variable or the actual numbers, if you wanted to put 2 or -1 into these functions, you just have to substitute them directly into these functions themselves and then figure out what they would be. Right? That's where we're going to end for 2.6.